Go ahead. I'm gonna record this as well. So obviously, same class. We're still talking about descriptive statistics, and specifically, what we're going to talk about today is measures of center and measures of variation. Right. So first things first, we have collected data as usual, and the question is now, what are we going to do? So we've collected data, and again, what do we say some of the important characteristics of data are to describe? Who remembers? It was a little acronym thing that we used. Who remembers what it was? Acronym might be the wrong word.
Was it
Center, variation, distribution, outliers, and time.
Very good. Center, variation, distribution, outliers, and time. Right? So those are the characteristics that we usually are going to try to describe about a data set. And today we are going to talk about these two right here. Center and variation. So we already talked about the distribution of the data set a bit, right? But today we're going to talk about center and variation. And we're going to touch on outliers a tiny bit. I'm going to just mention them a little bit. So again, that's CVDOT. And I'm actually going to... Do I want to play this? So I don't know if I can... Okay, we're going to play this video, but I probably, when I send this... If I send this video to you all, I'm going to have to like cut this part out because this is somebody else's video. But let's look at this video really quickly. So the question here is, are you typical? That's the question is asking. There's some music that goes along with it, but I don't think we need the music right now. The music wasn't playing anyway, but I think that's perfectly fine. So the question is, are you typical? So the question is, who is the most typical person in the world, right? So I'm going to pause it really quickly. What would you all guess? If I said, what is the most typical person in the world? First, what does that mean? And what would you all guess is the most typical person? You're on mute. Everybody's muted.
As far as like male or female or...
Yeah, sure.
I have no idea. I ain't gonna try.
I think that's the most typical person is a male or a female.
Yeah, but which one? Do you think there are more males or more females in the world?
Females there.
More females.
More females?
You asked for that.
more females?
Yeah.
Yeah, more females? Okay.
Males?
And what race would you guess that person was? So y'all said female. What race would you guess the person was?
Chinese.
Okay, some kind of Chinese. Why?
Asian.
Because that's
European.
the largest population, right, in the world. Is either, I'm pretty sure it's China has the largest population in the world. So probably some kind of Chinese. How old would you think they are? What do you think is the most common age in the world? If you all had to guess.
50.
I don't know why, but I want to say 35.
35? 25? Okay. Somebody said
35.
50? 35? Okay. Interesting. All right. And so we're basically looking at a 35 or 25-year-old, whatever age, female person from China. Right? That's what it looks like I'm getting from you all. Right? Some middle-aged female person from China.
The data gets skewed because the Chinese had that whole period where women weren't wanted, so they
see that it's not going to be as we expect. That's what we may see. So let's watch the video and see what it says. So first, they're saying it's a right-handed person. So most people in the world are right-handed. Most people in the world make less than $12,000 a year. They have a cell phone, but they don't have a bank account. This is the most typical person because they're saying less than a quarter of people in the world have a bank account. So what does he look like? Yes, you all were wrong. It's a male. Male is the most typical person in the world, but only a little bit. And their age is 28. So you all, I think, were on the right track with the age.
25 that we were close.
And Chinese, y'all were definitely on the right track with that. And so based on these traits, the most typical person is a 28-year-old Han Chinese man. And what they did actually is they used some kind of face averaging something to look and see what that person would look like. So they created an image of what that person would look like. And this is basically what the world's most typical person would look like, according to whatever research they had done. And they're saying that that won't be, because obviously populations change, etc. So they're saying it won't be the most typical forever. And that by 2030, India is going to overtake China, right? And this is a very important point. They said typical is always relative, right? Y'all notice that? The little height part? Let me go back a little bit. So it's relative. So in some places, like in Holland, the average height is 5'11", but in Peru, the average height is 5 feet 4.5 inches. And in Japan, average lifespan is, 89 years? But in Afghanistan, it's 45 years, right? And the amount of water people use changes drastically depending on what region you're in, right? And honestly, all of this stuff kind of changes drastically depending on, where you are or what population you're looking at. So I'm going to pause it there. That, I think, is kind of the important thing there. That when we saw what typical means, and we had an idea for some of those things, they're talking about like the average of all of them, but for some of them, they're talking about like who appears the most, right? For some of them, they're using kind of an average, like where the middle is, or who. Honestly, all of them is where the middle is, or who appears the most, right? That's what they're using to quantify who is typical, right? And an important word in there is that typical was relative. And this piece is going to come back again, but again, it means that it depends on what population you're looking at. So what's typical will be relative to the population you're looking at, or even the sample that you take from the population, right? So typical, another way of looking at typical would be to say who is in the middle, right? That would be a way of looking at typical. So when we're talking about the middle, we're talking about the center of a data set. And there are three main ways that we can describe the center of a data set. Way number one is the mean. 2 is the mode. 3 is the median, right? So 3 different ways that we can describe what is in the middle of a data set. 3 different ways. So getting started with the mean, we already introduced the mean. The mean is basically the average, right? And it's the average that we know and love that we already have. So the mean is basically when you add up all the numbers and you divide by how many there were. Add them all up, divide by how many there were. And one thing about the mean is that it tells us what we call the mathematical center. The reason why we say it's the mathematical center is because we got it by adding up the values. That's how we got it. We added up the values and we divided, right? And the mean does another thing where it considers every single value in our data set, right? And that includes extreme values. So if we have, we were taking the average height in this classroom, right? And let's say we had someone walk in and they're like 7 feet 5 inches tall, that's gonna shoot our average height way up, right? Because that person is super, super tall. So the mean considers every single value regardless of how big or how small it is. And because of that, because it considers every value, we say that it is not robust. So don't think about not robust as necessarily a bad thing, but it's just an understanding thing. And basically not robust means that if you have some extreme value or some outlier, it's going to move where the mean is. Right? It's going to move it up or move it down if you have some extreme value. Now, in Excel or Google Sheets, this is what we use to calculate the mean. We say equals average, and then in the parentheses, we put the numbers that we want to find the average value of. Right, so this is a basic idea. We already saw this slide where we said the formula is basically adding up all of the values that are in our thing and then dividing by how many there are. Right, so we add them all up and then we divide. And again, remember there were two different ways that we could have a symbol to represent the mean. We could have x bar or mu, where x bar, right, is a sample mean. Let's erase that. X bar is a sample mean, right, and mu is a population mean. So x bar tells us about a sample, and mu tells us about a population. X bar is a sample, mu is a population mean. And it's important to know the distinction between the two. All right, so if we're talking about a sample and we want to find the mean of the sample, we use x bar. But if we want to find the mean of the population, we use mu. Now, next we're going to talk about the median. I know we had said mean, mode median, but we're going to talk about the median.
Excuse me, can anybody hear? I can't hear anymore.
I can hear.
I can hear
I can
you,
hear.
but I don't think us responding will do anything because if she can't hear us.
Oh,
Tawanda, can you hear?
She can try using earphones because that happened to me last class.
Well, you couldn't hear anymore?
Yeah, and I had he told me to hang up and call back in.
And that didn't work either?
It worked.
But if she can still hear, if we can still hear her, it makes me feel like her volume is just turned down or something like that.
She can call out and call back in and try that. I think that
I'm
works.
trying to do the little chat thing. Or what she could do is, what do you say? Okay, so we're going to continue. And I just hope she sees that. But we're going to go ahead and continue. I don't want to keep you all night. So the median is the next one that we're going to talk about. And the median is different from the mean in that the median splits the data directly in half. And it's particularly when it's in order. So it has to be in ascending order. But it splits it directly in half. So if we were in the classroom, right, what I would do is I would actually have you all line up in height order. Right? And then we would find who the median would be. So that is obviously something we can't do with the social distancing. But that is what we would do. So with these people lined up, the median is the person that's in the middle. Doesn't matter how tall the people are. The median is the person in the middle. Who's in the middle here? So let's give them numbers. 1, 2, 3, 4, 5. Who's in the middle?
3.
3. Yay, they're our lucky median. That's our median. So the median is the person in the middle. Now again, it's very important. The median, it doesn't matter how big or how small the values are. These people could be 12 feet tall, right? Maybe this person's 12 feet tall, this person is 2 inches tall. It doesn't matter. The middle is still the middle if they're 5 people, right? So what if I did this? If instead of making this person this tall, what if I made number 5 this tall? Is the median still the same?
Yes.
Because it's still the same person in the middle. What if I made number 1 which one of y'all is short? Who's a short person? Jocelyn, you kind of short. So Jocelyn would be number 1. What if I made number 1 this person here? Did the median change?
No.
No, it didn't change. So that is why we say the median is robust, right? Because it doesn't matter how big the extreme values or how small the extreme values are. The middle is still the middle, right? Crystal, you're tall. Wait, Crystal, were you in my class before? I can't hear you. You on mute. If I
She's
don't,
muted.
yeah, you muted. If I remember correctly, Crystal, I feel like you was tall.
Now my
Say it. No, you like frozen a bit. Let me see. Who looks tall? Ashley, are you tall?
Did something happen?
Yeah, Tawanda, you got cut off a little bit there. I'm trying to find out, but I feel like maybe everybody's going a little choppy. Ashley, can you hear me?
I can hear you.
You can hear me. Yes. No, Jocelyn.
I can hear you.
Oh, I asked you if you was tall, Ashley.
Oh no, I'm not. I'm only 5, like 1.5.
Oh man, I was looking for a tall person. I was saying I remember Crystal. I feel like Crystal was in my class before. I feel like you was tall, but I can't remember.
No, I'm real short.
You real short, Ashley? Okay. So it doesn't matter. But again, it doesn't matter how big the tall people are or how small the short people are. The middle is still the middle if the number of people are the same, right? So that's why we call it robust, because it's not affected by the size of the smallest and the biggest one. Whereas with the mean, because we have to add in all of this tall person's extra height, right? When we add up all the height, we have to add in the tall person's extra height. And when we add in that tall person's extra height, what are they going to do? They're going to move the mean in their direction, right? So the mean is not robust because it is affected by outliers or extreme values, whereas the median is robust because it doesn't care how big the values are. All it cares is what place in line are you. That's all it cares. What place in line are you? Right? So that's the mean and the median. Both different ways of measuring what is in the middle. That's what they both are. Different ways of measuring what is in the middle. So for the median, to find the median, we already did this kind of example relatively straightforward. But what about when we actually don't have 5 values or an odd number of values? What if we have 6 values or 8 values or 12 values? How do we find the middle point then? And to find the middle point, when we have an even number of values, right, we have to find the 2 middle values. And in this case, what would the 2 middle values be?
Middle.
2 and 3.
2 and 3 are the 2 middle values, right? And what we do is we average the 2 middle values to see what's exactly in the middle of them two. So that's why we did 2 plus 3 divided by 2, because we're finding the average of those 2 middle values. So if you have an odd number of values, it's just whatever splits it exactly in half. But if you have an even number of values, it's the average of the 2 middle values. All right, so do 2 different ways of calculating the median, or you just put it in Excel and you type in median and it'll tell you the median, right? You type in median, select what you want to find the median of, and it'll tell you the median. So moving on. And again, this is all in the slides, so yeah. Now another interesting point about the median is because it's the midpoint, right? It's in the middle, 50% of the values are below it and 50% of the values are above it, right? That's what is happening with the median, right? Half of it is below it, half of the values are, well, not half, but yeah, it's basically splitting it down the middle. I'm just going to leave it at that. 50% of the values are below it, right? Not 50% above it. 50% of the values are below it, or it is bigger than 50% of the values. So moving on, here's just a little kind of summary of mean versus median. Again, the mean considers the value of the data point, whereas the median doesn't care about the value and only cares about the place in line, right? The mean is not robust for that reason, whereas the median is robust for that reason, right? The mean is better to use if there are no outliers or extreme values. So if there are no outliers or extreme values, then we want to use the mathematical center. On the other hand, right, if there are outliers or extreme values, then we want to use the median. All right, so depending on the data set, it might tell us which one we want to use. The mean can only be used with quantitative data. Only. We cannot find the mean of qualitative data. Doesn't matter if it's numbers. You cannot find the mean of qualitative data. The only exception that I will make for that is if we have qualitative data that are numbers that are also ordinal, where we can put it in a meaningful order. So for example, with the anxiety level or the pain level, because it's qualitative, but we can put it in an order and it is numerical, we can treat it like it's quantitative. So that would be an exception where we can find the mean of a qualitative data variable. But in every other example, every other situation, and just in general, you cannot find the mean of quantitative data. For the median, we can find the median of quantitative or qualitative data as long as it is ordinal. So we can put it in order, even if it's words, we can find the median or the middle point.
Professor?
Question?
Yeah, so you said we cannot find the mean of quantitative data?
We cannot find the mean of qualitative data.
Oh, quality, okay.
Yeah, if I said quantitative, I just made a mistake in my words. We cannot find it, because think about what the mean is. The mean is adding up a bunch of things. And if you got words, can you add up a bunch of words? No, you can't, right? So that's all I was trying to say. You cannot find the mean of qualitative data. You can only use the mean with quantitative data. So I might have said it backwards. And then two ways of representing the mean. We can either use x bar or mu. And for the median, this little symbol up here, that little squiggly, right? We call that a tilde. So this would be x tilde, right? This one is x bar because there's a bar over it. This one is x tilde because there is a tilde over it, a little squiggly, right? So this is x tilde or x squiggly. You can't really call it x squiggly, but that's a way to remember it. And x tilde is the median of a sample, whereas we'll use big M for the median of a population. So that's x tilde or big M. So moving on, the mode is probably the simplest of all of them to find. The mode is basically whatever one repeats the most. That's the mode. Just whatever repeats the most. And if there are two modes, right? If there are two modes, then we call it bimodal. And if there are more than two modes, we call it multimodal. But if there is no mode, as in no value repeats at all, then it is no mode. Like that's literally what we call it. We say no mode if no number repeats. So that's important. If there's no number that repeats, then there is no mode. If all of the values repeat the same amount, then it's multimodal, right? So you're looking at repetition, right? So no mode is when there's zero repetition. And I mean, that's all there is to say about the mode. It's just whatever value repeats the most. So what will be the mode in this list down here? These numbers down here, what will be the mode?
72.
72. 72 repeats the most. There are other numbers that repeat, but 72 repeats the most. And to say what the mode is, all you have to do is just say the mode equals 72. That's literally all you have to do. The mode equals 72. So let's talk about the connection between where the center is really quickly and skewness, right? So if we just recall, these were all different measures of modality, and these were all different measures of skewness, right? And you can kind of get an idea and see what's happening here. Bimodal means that you have multiple different places where you have a lot of repetition. That's what bimodal means. Multiple different places where there's a lot of repetition. Multimodal right? Multiple different places where there's a lot of repetition. Unimodal, everything is just kind of centered in the middle. And uniform, almost everything is repeating in a similar way, right? Then we have skewness, left skew, right skew, and symmetric, and we're going to connect that again as well. So when we talk about skewness, if we have a symmetric distribution, right, then we're going to use, if it's symmetric, this is an important point. If it's symmetric, then you can use the mean, right? That's what we want to use. We want to use the mean as our middle. But it doesn't really matter, because if it is symmetric, then the mean, the median, and the mode will all be basically the same if it is symmetric. So if it's symmetric, the mean, the median, and the mode will all basically be the same. And then if the distribution is skewed, right, or if it has really, really extreme values or outliers, then we're going to be more likely we want to use the median instead if it's skewed. And in the case of it being skewed, when it's right skewed, the mean is bigger than the median, which is bigger than the mode. But if it's left skewed, the mean is less than the median, which is less than the mode. It's a very simple idea. I think it's just memory that's going to help you with that one. So yeah, that's kind of the connection between the values of the mean and the median and the mode and the skewness. So for example, if I told you that the mean of a data set was 82, that's X bar, and the median of the data set was 95, what kind of skew does this have?
Wait, which direction does it go?
Right skewed.
Not right skewed. Look at right skewed. Right skewed requires the mean to be bigger than the median.
So
the
left skewed?
Left skewed. Look at this. The median is 95. The mean is 82. The median is bigger than the mean. That means it's most likely to be left skewed. What if I said our mean was 51 and our median was 51.5? What kind of skew is this?
Oops.
Left skew?
Still left.
Left skew?
Are you sure?
Yeah.
Think outside of the box a little bit.
Hmm?
Right skewed.
No.
Would it be symmetric?
There we go. It would be symmetric.
Hmm.
Right? Why would it be symmetric? Are these numbers really, really close?
Yes, and they would
Yeah.
be in the middle.
They're really, really close. And they're both, look here what we said for symmetric. That little squiggly line means approximately. It doesn't mean exactly equal. It just means approximately. Right? And so for these two, 51 and 52 are basically the same. Right? What if we had something like this where X bar was 1.5 billion and X tilde was 1.8 billion. There's a big difference between 1.5 billion and 1.8 billion. There's a difference of 300 million. It's a huge difference. But what would you all think that this was? Is it skewed or is it symmetric? And if it's skewed, which direction is the skew?
It is skewed.
You said it is skewed?
And
Yeah.
Okay, which kind of skew would it be?
It's going to be, I think left.
Okay, so left skewed would be a good guess because the median is bigger than the mean. But when we look at it, because of the scale of these numbers, if there is a skew, the skew would be very slight because 1.5 and 1.8 billion are close together. even though 300 million is a lot, 1.5 and 1.8 billion, they're close. Does that make sense? Because the numbers are so large, right? It's like if you have $0 and somebody gives you $100, you're like, oh my God, thank you so much. I had $0. You just gave me $100. But if you were a millionaire and someone gave you $100, would you even care? Would you even notice? No, you'd just be like, I guess I'll stick this in my suitcase with all of my other millions of dollars, right? So the size of the difference, it kind of matters what scale you're talking about. When we look at this scale, these numbers are close. So there may be a skew. Again, this is not exact. There may be a skew, but if there is a skew, it probably would be a small one. So this would probably be really close to symmetric, right? So moving on, if we look at this one, what could we tell? This is distribution of the percentage of time actually spent taking notes in class versus on Facebook or Twitter. And here it is right here, percent of time in class taking notes. What kind of skew is this first? Look at the tail.
This is left skewed.
This is left skewed because the tail is over here. Here's the tail. Tail is on the left, so it's left skewed. And what do we say for left skewed? For left skewed is the what bigger than the what? Let's go back here. Left skewed.
The mean is bigger than the median?
The other way around. The median is bigger than the mean. So our mean should be less than our median. And yay, that was the correct answer. Right? So again, it's just about kind of looking at the shape, getting as much information as we can to kind of, figure out what we can figure out. And this is a little summary of what we just said. We don't have to repeat this, but it's just a summary of what was just said. Right? We're talking about skew and its connection to our measures of center. Now, the next thing that we're going to talk about is not just where is the middle, but how far away from the middle are you, right? So if you all were to stand in a line, anybody in here like 5'5"? Anybody like 5'5", 5'6"? So Kristen said she like 5'5".
I'm 5'6".
5'6".
Yeah,
So
I have.
if all of you all were to stand in a line, all the 5'5", 5'6" people are probably going to be in the middle, right? That's just, I think, like the average height. 5'5" or so is like the average height. So that would be who would be in the middle. For everybody else, a question would be, how far are you from the middle, right? So like, you know how you get an exam and you want to know the average score? The average score is the middle point. So let's say we have an exam, and let's say, well, it won't be my exam because everybody in my class, all of you all should be doing really well on the exams. But let's say we get our first exam, and you score 42 on the exam, right? So some people just be like, oh man, I scored a 42. It's so horrible. But what's a question that you would ask just to see how horrible it is? What would you want to know? You would want to know what? How did the rest of y'all do? Say it again. Somebody's gonna say something.
What did everybody else get?
What did everybody else get? Because if you get a 42 and everyone got around a 42, you don't feel so bad, do you? Because then you're like, that's not my fault. That's the professor's fault, right?
Mm-hmm.
But if you get a 42 and then everybody else is like, you're like, what'd you get? What'd you get? And everybody's like, yeah, I got a 90. Somebody else is like, yeah, I got a 95. I got a 100. And you ask everybody, you can't find another person that got anywhere close to a 42. Now you're starting to feel bad, right? So it's
You're
not
an outlier.
now you're an outlier, exactly. Now you're far away. So you're like, ooh, I really did bad, So the measure of what's bad is not always just as simple as, oh, a 42 is a low score. Because if you got a 42 and you ask everybody else what they got, and they all got 13s, you're like, what'd you get? They're like a 13, and somebody else like a 15, I got a 2, right? Then you're like, ooh, my 42 is like an A, because everybody else failed even worse than I failed, right? So knowing where the middle is important, but you also want to know how far are you away from the middle, right? Are you just average? Are you better than average? Are you lower than average? And how much lower or how much better? So we call that, right, that idea of how far are things away from the middle, we call that variation, right? And there are 4 different ways that we can measure variation in a data set. 4 different ways, right? The first way is with what we call the range, right? That's probably the easiest way. And then we have the variance, and then we have the standard deviation, and then we have the IQR. IQR stands for interquartile
It's like your
range.
screen is it's big. Actually, you know what? I'll just move my screen over. Never mind. Go ahead.
Say that again?
No, never mind. Go ahead. I figured it out. I'll just move my screen. It was like your screen had gotten bigger, your presentation, but I'll just make my screen bigger. It's okay. Never mind.
Okay.
Sorry.
So yeah, that's what we're looking at. These 4 things are how we can measure variation. And that variation gives us an idea of how far, not just how far we are away from the middle, but how far everyone is away from the middle. Right? That's what it gives an idea. How far is everyone away from the middle? Is everyone really, really squunched in close? Or is everyone very, very far? So let me ask you all a question. Which of these groups would you all think have more variation? Now, I don't feel like drawing out people. I'm just going to draw little lines, right? Which group versus which of these groups do you all think has more variation?
The second group, yeah.
The second group, you can just kind of look at it, and I mean, it seems really obvious. But when you dig into it, what are we seeing? All of these ones are basically the same, right? So if we find the middle point, let's say this guy right here is the middle point. We find the middle point. Once we find that middle point, everyone else is likely to be where? Really, really, really close to that middle point.
Mm-hmm.
Whereas with the other group, right, with the other group, when we find the middle point, let's say this guy right here is our middle point, things aren't going to be as close to the middle point. We're going to have more variation in the sizes of the different sticks, right? More variation. So that's kind of what we're looking for. So with the first one, we have the range. And the range tells us about the spread, like how far spread the data set is, right? And that is important for a couple of different reasons. I'm sorry, this slide actually just talks about variation again, but the range does tell us about the spread. So again, this is basically what I just said with that example. So we're going to move past this a little bit. But another thing, just to mention really quickly, variation helps us to start analyzing the data set. Before, what we've been doing is we've been just describing the data set. Right? Measures of center, kind of just describing the data set. What we're actually going to be able to start doing after this is analyzing the data set. And another thing variation lets us do is variation lets us identify outliers. That's what variation lets us do, identify outliers. So first, the range, right? The range is telling us how wide the data is spread. So, for example, Trinity classes, all of my classes always have a wide range of ages. I've had students who were 19 in my classes, and I've had students who were 75 in my classes. A wide range. So one of my students in my first semester was 75. And I think she said she just wanted to go to school just because she was like, I've done a lot of stuff, and I never got my degree. I just want to get my degree. That's why she was in school. So I had students who were 19, students who were 75. That's a wide range. Now, CAS classes, like College of Arts and Sciences with the day classes, they don't have as wide a range or as wide a spread. Why don't they have as wide a spread? Because almost all their students are like normal college age, right? So all their students are somewhere between 19 and like 22, 23, right? Almost none of their students are outside of that, even if they do have a couple of students that are outside of that range. So the range is just saying how wide is the spread. And to find the range, all you need to do is do the maximum minus the minimum. It's the difference between the maximum and the minimum, and that gives you the range. So what is the biggest number? And then you take away the smallest number. That's the range. The range is not robust because since the range uses the biggest number and the smallest number, obviously if you change the biggest number or the smallest number, it will change the range. And if you change the biggest number or the smallest number, and if it affects the measure that we're using, then we say it's not robust. So the range is not robust because it is affected by outliers. It's affected by extreme values. So moving on, we have a way of measuring, because remember we said we wanted to measure how far we are away from the center. But there were different ways for us to measure what the center was exactly, right? There were different ways for us to measure it. So we could measure how far we are away from the mean, or we could measure how far we are away from the median. So we're going to start off with the standard deviation. Standard deviation and the variance, which are both two sides of the same coin. Standard deviation and variance tell us about how far, not how far we are exactly, like an individual person is, but on average, how far are things away from the mean. And I know there's a lot of averages, but on average, how far is stuff away from the mean, right? So the process, right, for finding the standard deviation is basically finding how far each thing is away from the mean and then averaging those numbers. So for example, how tall are, let me get everybody's heights. How tall are you, Manua?
5'8".
5'8". That is not a pen. 5'8". We'll use numbers. 68 inches. Kenita, how tall are you?
5'6".
5'6". That'd be 66 inches. Jocelyn, how tall are you?
Not sure, but I guess 5,
5 feet?
maybe.
60 inches. Crystal, what'd you say? You said 5'5"?
Yes.
Okay. Gabriella, what about you? Gabriella, can you hear me? Oh, it looks like she's doing something else. Sarah, what about you?
I'm 5'3".
Ashley, what'd you say? I think Ashley said 5'1".
Sarah,
I'm like 5'1.5", but we can round it up to 5'2".
You're trying to be a little taller. Okay, Tawanda, what about you? How tall are you?
5'7".
Okay, so we'll just stop there. We'll use these people as an example. Now we need to find the average. How do we find the average? We add all these up and we divide by what? I think we did 7 people. So we add it all up, divide by 7. So we're going to do 68 plus 66, so on and so forth. So I got 451, and then we're going to divide by 7. So I got the average, or the mean, being 64.4 inches. That's what I got as the mean, 64.4 inches. Now, you didn't get that? Somebody didn't get that?
I got it.
Okay. So now what we're going to do is we're going to find out how far each of these are away from the mean, right? So we're going to take each of them and we're going to subtract the mean, minus 64.4, right? Let me do it this way. Minus x bar, 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 minus x bar. And basically what this is going to do is it's going to tell us how far each one is away from the mean. And I'm going to kind of summarize it a little bit, but the process of finding the standard deviation is after we find out how far each of you all are away from that mean, how many inches are you away from that 64.4 inches? Are you taller than it? Are you shorter than it? And if so, how much? We're going to basically be looking for a way to average all of those values out. That's basically what we're looking for. A way to average all of those distances out. And when we average all those distances out, with a little bit of math trickery in there, right, we get what's called the standard deviation. Actually, what we do is we get what's called the variance. When we average all of those out, we get the variance. And then when we take a square root of that, we get the standard deviation. But you all get the idea. The idea here is just for you to understand where it comes from, right? What it is, what the process is, or what it is that it's measuring. So you can see that if you have a bunch of values, right? If you have a bunch of values that are like really, really, really far away from that middle point, then you can see that that standard deviation is going to be larger because all of those little distances are going to be larger. All those little distances from the mean are going to be larger. On the other hand, if you have ones that are really, really close together, then our standard deviation is going to be smaller. So going back over here, the main thing I want you all to do, I want you all to focus on how to use technology to calculate both the standard deviation and the variance. And I want you to focus on that just because, you know, I just don't think it's worth focusing on. I'm going to show you the formula for how to calculate the standard deviation, but it's just not worth it right now. And I'll probably send you all like a little side video that you can watch on how to calculate the standard deviation by hand. But none of my exams are going to require you to calculate the standard deviation by hand. And I want you all to focus on what the standard deviation is telling us, not on figuring out the calculation by hand. So this is an example of going through calculating the standard deviation. We're going to move past this, right? But the one thing I do want to show you, this actually calculates the variance, and we actually have to take the square root of it to get the standard deviation, right? So this down here is what I wanted to show you here. S is the standard deviation of the sample, and the variance is S squared. So if we take the standard deviation and we square it, we get the variance, or if you take the variance and you take the square root, we get the standard deviation. And this symbol here is sigma. Sigma is the population.
Yes. Thank you very much for holding. I do appreciate your patience. So I did get a representative from Silver and Fit, and I provide.
I think she's having a whole meeting while she's talking to us. Okay. Anyway, don't have meetings during class, but I understand. Today I had 3 simultaneous meetings at the same time. I had one going on my iPad, I had one going on my computer, and one going on my phone. And every time I had to like speak in one of them, I would just mute everything else, turn the volume down, say what I was saying, and then go back. But yeah, I understand. You got to get work done. But if you can, try to save it for not during class. But anyway, moving on. This symbol here is sigma. That's what that symbol here. That's a sigma. That's how we say that. That's the population standard deviation. And if we square it, we get the population variance. If we have the variance, we have to take the square root of the variance to get the standard deviation. So it depends on which way we're going. The main thing that we use in like practical terms, we use the standard deviation in practical terms. Right? You're almost never going to work with the variance. We're usually going to work with the standard deviation. Right? And another important note is that the standard deviation has the same units as the original values. And again, the standard deviation is telling us, on average, how far are things away from the mean. On average, how far are things away from the mean. So therefore, if our standard deviation is larger, then that means things are further and further and further away from the mean on average. Whereas if our standard deviation is smaller, that means things are really, really close and compact around the mean. Right? And one other note is that the sample standard deviation is calculated differently from the population standard deviation. And that's important because even technology, if you use Excel or something to find the standard deviation, you have to choose, am I doing the sample standard deviation or am I doing the population standard deviation? And both will give you different results. Obviously, if it's a sample you're looking at, do the sample standard deviation. Whereas if it's a population you're looking at, do the population standard deviation. Another little note in there. Yeah, I'll just leave it at that. But yeah, we're going to basically use technology to find the standard deviation. I just want you to understand what that means. So I don't know why it looks like my slides kind of got a little jacked up with the pluses and the minuses. If any of the slides you all download look a little weird, just send me an email and I'll try to correct it. But this is just looking at the sample standard deviation versus the population standard deviation, with sample variance versus the population variance. And the idea is that we just divide by something different in both of them. And it's just to make it more correct. Now, in terms of saying what is considered far away from the mean, right, we can use the standard deviation to say if something is, I'm going to say quote unquote, far away from the mean. So if something is 2 standard deviations or more away from the mean, then we say it's far from the mean. And if it's 3 standard deviations or more, then it is probably an outlier. Doesn't mean it's necessarily an outlier, but it is probably an outlier. We have a special rule that tells us how much of the data set we should expect to be close to the mean. All right, we have a special rule. And that rule is called the empirical rule. Now, really quickly, I do want to just give you all an example. And this example is a little more, or this analogy is a little more relevant when we can do it in person. You can actually see me. What I want you to imagine, you're at a bar with your friends, right? That's what I want you to imagine. You're at a bar with your friends. And I want you to think about if you all were sitting at the bar, just you and your one friend, I want you to think about how many seats would have to be between you for you to be like, why are you sitting so far away from me? If somebody was sitting the seat next to you, they're not far away, right? They're pretty close. What if someone was sitting 1 seat over? So there was you, a seat, and then they're in the next seat. You know, that's still not that bad, right? I mean, you can have a conversation with 1 seat in between you, correct? Mm-hmm. Now, what if there are 2 seats in between you and your friend? Then if there are 2 seats in between you and your friend, then you and your friend might as well just be like Molly or Issa. You know, that's who y'all are. Any of y'all watch Insecure?
Mm-hmm.
Yeah, that's who y'all are. Y'all are Molly and Issa if y'all 2 seats in between y'all in the bar. Now that's just weird. Y'all are far apart if there are 2 seats in between you, right? It's the same thing with standard deviations. Think about the standard deviations being a seat at the bar, right? And if you're trying to hold the conversation and it's 3 standard deviations in between you all, that's awkward. They're really far away. Why are they being an outlier? I mean, on the flip side, you could think about a group of friends at a bar, right? And if there's a group of friends at a bar, at least in every friend group I've ever seen, there's always like a person who's kind of like the bridge between everybody. Or maybe they're the funniest person or something like that, or they're the center of the conversation. And that person might be in the middle. And if that person's in the middle, and you're like 4 seats away from them all the way on the edge, you're like, okay, I'm far. You're trying to lean in to hear the conversation. You might even stand up and just go walk over there to the middle of the group, right? So that's an example. Use a bar stool and just say, okay, how many bar stools are there between the middle and where the person is, right? And that's what we're using to say if something is far away from the mean. So this is the empirical rule. Looks like a lot, it's not as much. And the way I'm going to show you it not being as much is like this. This point right here, first, what kind of distribution does this look like? Imagine, you can't see the bars here for the histogram, but this is like the shape. What kind of distribution is this?
Bell-shaped.
So it does say bell-shaped up there. What are the other names that we had for it?
Symmetric.
Symmetric. We fold it in half. It's exactly the same on both sides. So symmetric or normal or bell-shaped. So for this kind of distribution, this middle person, that's the center, right? Think back to our bar example. That's the center of conversation. That's the funny guy. That's the person who got all the stories or whatever. Or maybe y'all, the rest of y'all didn't really know each other, but all of y'all know this person, so y'all all there, because y'all all know that person. This would be going to the left or getting less than or smaller than that person, but just think about it as going to the left. And this would be going to the right. So it doesn't matter which side you're on, we're just counting how many standard deviations or how many bar stools you are away from that person. And what we're going to measure here is we're going to look at like an actual friend group instead of just an individual person. And the empirical rule tells us is that when we have a normal distribution, within one bar stool, meaning sitting right next to the middle, one bar stool or one what? Standard deviation from that middle person, there will be 68% of the data. 68% of the friends or the friend group will be sitting that close to the person, right? That close to the middle, 68%. And if you're talking between two bar stools, right? Two bar stools on either side, 95% will be within two bar stools of that middle person. 95% of the data will be within two bar stools. And if we're talking three bar stools, then 99.7% of the data will be within three bar stools. Now I rounded it off because this is 68, 95, and 99.7. Okay? 68, 95, 99.7. And what you can see that most of everybody, if you go out with your group of friends, everybody's going to be sitting within three bar stools. Almost everybody will be within three bar stools of the middle person. Almost everybody. And then once you get outside of that range, now you're getting into like, why are you sitting all the way over there? Right? Once you get outside of that range. That's what the empirical rule is telling us. It's telling us how much of the data will be within a certain amount, right, of the middle point. So for example, let's say our standard deviation was 2. Let's go back over here actually. Let's say our standard deviation was 2. Right? So S equals 2. Let's say our mean, because again, the standard deviation is telling us only about how far things are away from the mean. Let's say our mean is 50. Right? So 50 is in the middle. We can go one standard deviation more and one standard deviation less than. And that would be considered one standard deviation away from the mean. So if we went one standard deviation more than 50, where would we be?
52.
52. And if we went one standard deviation less than the mean, where would we be?
48.
48. And what the empirical rule is telling us, that in this range right here, highlighted yellow range, 68, I'm going to write it in a different color, 68% of all of the data that you collect, if this is a normal distribution, 68% of all of the data that you collect will be between 48 and 52, right? 68% of all of the data will be between 48 and 62 and 52. And if you go out to two standard deviations, right? If we go another standard deviation out, where are we going to be at? One more
46 and 54.
46 and 54. So this would be 54. This would be 46. And what we're saying is that from 46 to 54, which is how many standard deviations from the middle? That's two standard deviations from the middle, right? 2 standard deviations this way, 1, 2. 2 standard deviations this way, 1, 2. 2 standard deviations from the middle, right? The empirical rule tells us that 95% of all of the data will be within 2 standard deviations of the middle point, right? Let me actually change how I'm writing this a little bit. So what I'm going to do, and I'm going to put my 68% right here. 50 is the middle point. I'm going to put that right up here. 50 is the middle point. I'm going to put a little box around 50. That's the middle. And then I'll re-highlight it. So 68% of all the data is between within 1 standard deviation of the mean. So you collected all of your data. You know it's a normal distribution. You know the standard deviation. You can say 68% of all of that data will be between 48 and 52. And then we have the last level, which would be another one. If we went another standard deviation that way, what would it be? 44. And if we went another one this way, what would it be? 56. Right? So we went another standard deviation. Now we're going from here all the way over to here. 99.7% of all of the data that we collect should be between 44 and 56. 99.7% of all the data we collect should be between 48 and 56. And that's basically what it's telling us. That's what the empirical rule tells us. It's a very important rule. And another thing that this could tell you, because this is again specifically for normal distributions or symmetric or bell-shaped. These are all the same thing. This is for this kind of distribution. So this takes us back to why it's important to do a histogram, because the histogram tells us what? It tells us what kind of distribution we have, doesn't it? Mm-hmm. And once we see that it's one of these distributions, we know that this rule applies, right? That's what we know applies once we see that it's this kind of distribution. So that's what we're looking at when we look at the empirical rule, right? We're looking at how much of the data, and again, that 50 is the person who's in the middle, and we're saying 68% is within 1 standard deviation, 95% is within 2 standard deviations, 99.7% is within 3 standard deviations. So that's the empirical rule. It's not all that complicated. We're going to talk about this other rule some other time. I'll probably mention it next week. We're going to talk about that other rule a different time. So moving on, that was how do we find it. We'll probably only go for like another 15 minutes maybe. I know this was a long class tonight, but we'll only go for like another 15 minutes. So moving on, we were just looking at how do we find how far things are away from the mean. Well, now we need to say, well, how far are things away from the median? And to find out how far things are away from the median, we use what we call the interquartile range, and we construct what we call a box plot. Now, quartiles, right, are basically markers in our data set that split the data set into 4 quarters. That's why it's called quartiles. It splits the data set into 4 quarters. Right? So if we draw stick people again, 1, 2, 3, 4, 5, 6, 7, 8. Let's do 9. 9 stick people, right? Who's in the middle? Number 5 is in the middle. Number 5 is in the middle. And then we could find the middle of the bottom half and the middle of the top half. The middle of the bottom half would be right in between these 2 people. And the middle of the top half would be right in between these 2 people. Now, what do we notice? 2 people here. 2 people here. 2 people here. And 2 people here. So we split it into 4 equal parts. I'm going to draw another picture like this again, because this came out a lot more choppy than I thought it would be. But I'm going to draw another picture like this again. But hopefully you were able to get the idea. But we're going to draw another picture like that. But that is what the quartiles are doing. They're breaking it into 4 parts. Breaking our data into 4 parts. Right? So Q1, or the first quartile, is basically the bottom 25%. And it's saying, at this marker, 25% of the values are less than me. 75% of the values are greater than me. Q2 is in the middle. 50% of the values are less. 50% are on top. Q2, or the second quartile, is also called the median. They're the same thing, right? Because it's just looking at the place in line. So Q2 is the median. And then Q3 would be 75% of the values are less, right? And 25% are more. Question, should there be a Q4?
Yes, 4 quarters.
Almost, but think about it this way.
The 4 quarters is the whole set.
The whole set is 4 quarters. But how many lines do I need to break this into 4 pieces? I only need 1, 2, 3 lines, right? And those 3 lines, they break them into quarters, 25%, 25%, 25%, and 25%. But there are only 3 quartiles, Q1, Q2, or the median, and Q3. Right? So this is what our quartiles are doing. The interquartile range, or the IQR, is basically just Q3 minus Q1. The third quartile minus the first quartile, which is basically saying how wide is this space in the middle right here. That's what the interquartile range is asking. Right? How wide is that space in the middle? And we can also call that space in the middle 50, the middle 50% of the data. Right? So it's saying how wide is the middle 50% of the data. And that's what we're asking. Sometimes, again, you call that space between Q1 and Q3 the middle 50. So moving on, this is a visual thing. We kind of just drew that a bit. But an easy way to find Q1, Q2, and Q3. Finding Q2 is easy. That's just the median. That's what's in the middle. But to find Q1, we can just find the middle of the bottom half. And to find Q3, we can find the middle of the top half. Right? That's all we have to do to find Q1, Q2, and Q3. Middle of the bottom half is Q1. Middle of the top half is Q3. The middle of everything is Q2. So start off, find the median. After you find the median, look at the bottom half of the numbers. And what's in the middle of the bottom half? That's the median of the bottom half is going to be Q1. And then the median of the top half is going to be Q3. All right, so that's basically what we're trying to do. And then moving on, we have a box plot, which is basically something we can construct that will show us outliers and will also give us kind of a visual representation of where most of the data is. So the box plot, the box, which is this part right here, the box represents the middle 50. Since it represents the middle 50, this line is Q3. I wrote Q1. This line is Q1. And the line that's in the middle is our median, or Q2. Right? This line up here and this line up here are markers that either show us the largest number or they show us 1.5 times the IQR. It's just a limit. we take the IQR, Q3 minus Q1, multiply by 1.5, and that's the marker there, right? Plus Q3. And this one would be 1.5 times the IQR, right? Q1 minus that, right? So that's how the basics of how we're constructing the box plot. Anything that's bigger than this value here is going to be an outlier. All those are outliers. Anything that's smaller than this value here is going to be an outlier, right? And I kind of wrote all of that out. I just wanted to show you. But the upper whisker, right, and the lower whisker, we call these things whiskers. So this point up here, we call it a whisker. And if you look at it sideways, you can kind of see why. It's like little whiskers poking out the side. Right? That's why we call it whiskers. But the top whisker, again, we're finding that top whisker by doing 1.5 times the IQR plus Q3. And we're finding that bottom whisker by taking Q1 and doing Q1 minus 1.5 times IQR. So space in between here and here is 1.5 times the IQR. And the space between here and here is 1.5 times the IQR. Now in this case, the bottom whisker, there were no values that stretched all the way down there. So if there are no values that stretch all the way down there, then you just do the bottom whisker at the lowest value that there is in your data set. So either it's going to be the lowest value or it's going to be that lower whisker value, right? So again, this is how we're finding that upper whisker and that lower whisker. We're finding how far it's going to be by doing either this or this to find the lower whisker or the upper whisker. Right? So let's do an example really quickly. Right? Let's say we are constructing our box plot, and let's say we have, these are our numbers, 0, 1, 3, 7, 10, 12, 15, and 19. First, what number's in the middle?
10. No. 1, 2. 1, 2, 3.
No, it's 10.
Nope, not 10.
10. Well,
Well,
Eight.
whatever's between
yeah,
7 and
yeah.
7 and 12 out.
whatever's between 7 and 10.
Exactly. So we need to do 7 plus 10 over 2 to find our median. And what's that going to be?
That's 17.
It's going to be
That would be
8.5.
16.5. Oh, 8.5, sorry.
8.5, right? So that's our median, or Q2. So now we know Q2, right? Now we can find Q1 by saying what is the middle of this bottom half and the middle of this top half, right? So what will be the middle of the bottom half?
5.5? No.
91343.
This bottom half. What's the middle of this bottom half?
2.
Now, there's an idea of an inclusive or exclusive quartiles when you go in Excel, right? But what we'll do is we're going to do it in the exclusive way, meaning we're not including that middle number. So, yes.
So 8.5 isn't included?
8.5 is not included in our bottom half.
Not included.
So, we're going to count it as 2, right? That would be 2, because that's in the middle of 1 and 3. We don't have to do anything else there. Yes, I know. I heard you. I heard you say 2. That's why I just continued. I heard you say 2. That's what you could say. I said that. Yes, you were correct. It was 2. And then for the top half, what's the middle of this top half? Between 12 and 15. $13.5 is between 12 and 15. Right, so that's the middle of our top half. So we have 2, 8.5, and 13.5. Now, really quickly, I'm going to introduce you to this idea that's really helpful when we do a box plot. And the idea is of a 5-number summary. So 5-number summary. It's really helpful. These are the numbers that we want to find to do a box plot. You do the minimum number, right? Then you list Q1, Q2, Q3, and then you say the maximum number. So what will be our minimum and our maximum is 0 and 19. And then boom, now we have the 5-number summary. 0, 2, 8.5, 13.5, 19. So now we want to construct a box plot for these numbers. So we know Q1, Q2, and Q3. I'm going to write out the 5-number summary really quickly. We have 0. What was it? 0. Q1 is 2. We have 8.5. 13.5. And then we have 19 as our max. So now we have our 5-number summary. We can go ahead and go about constructing our box plot. To construct our box plot, we need to find where those upper and lower whiskers are going to stretch to. So to find the upper and lower whiskers, we need Q1 and we need Q3. And we need to find the IQR. The IQR is Q3 minus Q1. So we have 13.5 minus 2. And what do we get? 11.5. So our IQR is 11.5. Right? That's our IQR. So boom, now we have the IQR. Now we need to find where that upper whisker is going to be and where that lower whisker is going to be. The upper whisker will be at the big one plus this. So it'll be Q3 plus 1.5 times the IQR, which is going to be what? 13.5 plus 1.5 times 11.5. Right? And what do we get? 1.5 times 11.5. 1.5, I'm just doing it in my calculator, times 11.5 is that plus 13.5. And we get 30.75 is what I got. So that would be the upper whisker. Kind of. We're going to look at it in a second. The upper whisker. And then for the lower whisker, we do Q1 minus 1.5 times the IQR. And we have 2 minus 1.5 times 11.5. And we get our lower whisker. So 2 minus 17.25. And we get minus 15.25, and that is our lower whisker. Right, that's our lower whisker. Now that we have our upper whiskers and our lower whiskers, we can draw a box plot. So let's draw a box plot. So first, let's just draw a vertical number line really quickly. Our number line will go from, well, we don't need to draw that. Let's just start by drawing the box. So here's the box. Right? This is going to be Q3, right? Q3, which is 13.5. This is going to be Q1, which is 2. And then in the middle, we'll have the median, which is 8.5. Right? Now we need to draw upper whisker. Now the upper whisker is going to be whichever one is smaller, right? The upper whisker will either be the biggest number, the maximum, or the number we just calculated. So let's look back at our data set. Which is the smaller one? Is the maximum smaller than the upper whisker?
Oh,
Look at our
Right
upper
here.
whisker. Our upper whisker is 30.75, but our biggest number is 19. So which is bigger? 30.75.
The upper whisker.
Exactly.
whisker.
So we're only going to draw our upper whisker to the smaller of the two numbers. So we're only going to draw it up to 19. The idea is just that we don't have numbers that are bigger than 19. So why are we drawing a line that goes all the way up to 30? Does that make sense, kind of?
Right.
Right? So we don't have numbers that go all the way up to 30. So we're just going to draw it. Up to 19. That's all we need to do. And that'll be 19. And then going down, we don't have numbers that go all the way down to negative 15. So all we need to do is go down to the smallest number that we actually do have. If we did have numbers that went all the way down there, then we would put them on there and we would go down to negative 15 or whatever it was. But we don't. So we're just going to go down to the smallest number. What's the smallest number? 0. So we're going to take our bottom whisker down to 0. That's how you get the whiskers that aren't the same size, because there isn't always going to be outliers, so to speak. So when we look at it, and now here is an interesting thing. Watch what I'm about to do. What if we changed our biggest number? What if we made our biggest number, instead of making it 19, what if we made it 100? If we made our biggest number 100, does that change what our median is?
Yeah. No,
No, it doesn't.
because the number in the middle doesn't change. It's just the ending.
Exactly. Just the ending changed. The number in the middle didn't change. So since that number in the middle didn't change, did any of our quartiles change? Did Q1, Q2, Q3, did any of those change?
No.
Nope.
No.
None of them changed. So let's look and see what we would do if, instead of our 5-number summary being this is our 5-number summary here. What if our 5-number summary was instead this? 0, 2, 8.5, 13.5, and 100. Right? So that changes the situation a little bit. How would we draw our box plot in this case? So the only thing we changed is that our biggest number is no longer 19. Our biggest number is now 100. So what do? Now what we're going to do is we're going to draw our middle point, our middle section. We have 13.5 is Q3. That's the top of the box. Q1 is the bottom of the box. In the middle of the box is the median, 8.5. Now our bottom whisker, let's start with that. That's still going to go down to 0 because we didn't change the bottom part. But where's our top whisker going to go to this time? So this doesn't change. This is not going to change here because none of our numbers changed. So now our biggest number is 100. Now we do have numbers that go bigger than that upper whisker number, 30.75. So now in this case, we need to go up to 30.75. And then what we're going to do is we're going to put a dot all the way at the top. And we label the dot. When you look at the box plot, the dots are the outliers. The dots are outliers. That is how we find outliers. If we have any values that are bigger than that upper whisker, then it is an outlier. Any values bigger than that upper whisker is an outlier. Right? So does that make sense how we see that change between the two box plots? Does that make sense to you all? Y'all were able to follow that?
Yes.
So that's what we do. Now, when you're making it, again, if you have any numbers bigger than the upper whisker or bigger than the upper whisker or smaller than the lower whisker, put a dot to signify it. And all of the numbers that are bigger than the upper whisker or smaller than the lower whisker, we consider them to be outliers. So going back over here, which we're almost done, we only got like one slide left, right? Again, an outlier is one that is outside of that maximum reach of the other ones. They do have another value here where you could say you could do 3 times the IQR instead of 1.5 times the IQR. it's not a big deal. I mean, some people will say like major outliers or minor outliers, but again, it's not that big of a deal. We're gonna stick to the 1.5 measurement. You'll find a lot of stuff in statistics is kind of subjective. That's what you'll find. A lot of the stuff is a little bit subjective. And then we had like one more slide.
Turn on the light.
So why is it important to look for outliers? We want to look for outliers and be able to identify the outliers because, one, it can help us find extreme skews, right? For example, here, right, we had that 100. That's like an extreme skew. Imagine you were chilling with all your friends, and all your friends are like, yeah, let's go to this restaurant. And y'all are like, okay, how much money you got? One friend's like, I got $0 to spend today. Another friend's like, I got $2 to spend today. One person's like, I got $8.5 to spend, and another person's like, I got $13.5 to spend. So all of y'all are like, oh yeah, we're broke. We don't got no money to spend. And then out of the blue jumps Tawanda, and Tawanda's like, y'all broke. I'm trying to drop 100 tonight on this food that I'm about to go get, right? That's an extreme value. It's considered an outlier. So we want to be able to identify those extreme values. Also, we want to be able to identify data collection errors, right? Or entry errors. Either we collected the data wrong or we entered the data wrong. So, in fact, what it turns out is that Tawanda was just as broke as the rest of y'all, but when she checked her bank account, she saw 100, but it really said 10. So it was a data collection error. I'm sorry, Tawanda, to pick on you. If you there, Tawanda? I didn't know Tawanda's there.
I'm here.
Okay, yeah, I'm sorry to pick on you, but yes. So sometimes we just input the data wrong, and if we just input the data wrong, we want to identify it because we don't want it to, seriously affect the data that we're collecting. That's what we don't want to do. We don't want it to seriously affect it. Another thing is, let's say it's not an error. If it's not an error, then it will point us to some interesting stuff, right? So if you're measuring people's heights and you come across some outlier height and you got somebody who's 8 feet 9 inches tall, you're gonna be like, okay, let's study this really, really tall person, right? That's what you're gonna say. Okay, let's focus some information to see how did this person get so tall, right? And we actually call all the stuff that's within like a regular range or 2 standard deviations of the middle number, or within Q1 and Q3, or within the 2 whiskers, we call all that stuff normal, right? So if it's close to the mean, if we don't consider it far, or if it's within the whiskers, not an outlier, we just call it regular. It's just normal. That's what it is. It's just normal. It's a normal observation. It's not significant. That's what we said. That is a statistical term. Not significant is a statistical term, right? That's what we call it. We call it not significant. So yeah. And then very, very last thing that we're going to mention is just, again, mentioning that idea of robust or not robust, right? When we want to make sure that what we're doing is robust, right, in the sense that large numbers and small numbers aren't going to affect it, then we want to lean towards the median and the IQR because they will not be affected by skewness or by outliers. On the other hand, right, if we are using something if we have a distribution that's symmetric, then we want to use the mean and the standard deviation because the mean and the standard deviation are mathematical calculations, right? So that idea of robustness is very important. And the very last example I'll give you in terms of that idea is just think about if we were doing some measure that depended on salaries or something, right? If we were doing something that depended on salaries, would you want, like, let's say we were looking at, here's a real example. Let's say we were looking at what we would consider, who we would consider to qualify for, like, affordable housing or cheap housing or public housing or something like that. Let's say we were looking at who should we consider it. If we have a really, really rich city like DC, what's going to happen? All of the rich people in DC are going to skew, right? Let's say what we did for the housing is we said, okay, we're going to draw a box plot, or we're going to draw our distribution, and then we're going to make a cutoff point. So either we can draw a distribution like this, right, where it's normal, we add a middle point. We don't know if it's normal, but we add a middle point, and then we'll say we'll give the housing to everyone who is less than one below this marking here, 1 standard deviation and less. We'll give the affordable housing or whatever to. We'll let people who are below that point for income apply for it. Or we could draw a box plot, and we'll say we'll let everybody who's less than, this marker here, we'll let all of these people apply for the affordable housing. Which one of these do you think would be better to use in that kind of scenario? You're on mute.
The box plot.
Why do you think that would be better?
I'm thinking that this other one just shows too much of the overly wealthy people, as opposed to we want to get rid of those overly wealthy people.
Exactly.
Well, not get rid of them, but
we don't want to factor them in.
Factor them in.
Exactly. And that's the exact idea. And it's a very real example. And what you'll find is that people will switch it up. Sometimes people will use a mean and standard deviation to represent the middle point and how far things are away from the middle when there are outliers. But what are the outliers? What are those extreme values going to do? If they're a bunch of rich people, what they're going to do is they're going to pull the mean up that way. And if they pull the mean up that way, what's going to happen? It's going to make what you say is the average income be much higher, right? Which is actually something that happens pretty often. I mean, right now in DC, I think the what they consider affordable housing, that marking, you got to be like, I think it's like 90,000 or something, 95,000. It's a crazy high number, right? That where they consider people making less than this qualify for affordable housing, right? Whereas if you use the median is not going to factor in all of those rich people. It's not going to factor it in because the median just cares about how many people there are and what place in line are you. That's what the median cares about. So it really depends on what it is that you're looking at, what kind of data set you have. And that's why it always starts off with what is the shape of our distribution. If it's skewed, median, IQR. If it's symmetric, mean, standard deviation. That's a general rule of what you want to try to do. Right? So with that, we are all done. Anybody have questions about what we have up here?
I did not understand. Could you please explain the empirical rule again? I don't think I understood that.
Okay, so if we go back here to the empirical rule, we're looking at what percent of the data is within a certain number of values. So I did an example over here, right? The middle point is 50. And with that middle point, and this again only for normal or symmetric distributions, with that middle point, we can go up and down 1 standard deviation. So if we go up 1 standard deviation, where do we get? We get right over here to 52, right? And if we go down 1 standard deviation, where do we get? Over here to 48, right? And what the empirical rule tells us is that let's say we have a whole huge list of numbers, huge list of data that we've collected. With that huge list of data that we collected, if the data is going to be normal, 68% of that data will be in between 48 and 52 if 50 is the middle point. Likewise, if we expand it out to 2 standard deviations, which takes us up to 54 or down to 46, again, we said our standard deviation was 2, right? But if we expand out to 2 standard deviations away from the mean, then we are saying 95% of all of the data that we collect will be in between 46 and 54. That's what we're saying. That's what the rule tells us. 95%, right? At least 95%. Let me say it that way. At least 95% of all of it will be there. And if we have it such that we go out to 3 standard deviations, and we're saying that 99.7%. So basically, almost all of the data will be within 3 standard deviations of the mean, right? So that means only 0.3% of all of the data that you collect, right? Or if you collect 1,000 surveys or samples or whatever, only 0.3 would be what, three people? I think 0.3 would be. I think 1% of 1,000 is what, 10. 1% is 10, so 0.3% would be 3 people. So if you collect 1,000 samples, only 3 of them will be outside of that 3 standard deviation range. Only 3 of them. So that's what the empirical rule is telling us. So it's 68, 95, 99.7. How much of the data is within a certain number of standard deviations of the mean? Anybody else have questions? Questions? All right, so I'm going to go ahead and stop the recording.